Lorenzo Zambotti, and he will speak about entropic functional of families of random variables from theoretical biology. And
thank you very much. Thank you very much. So this is a joint work with a colleague, Jérôme Buzzi. He's a so I try in my life to be a probabilist, and he tries to be an expert of ergodic systems, so say dynamical systems, and he found so he was reading a book on say theoretical biology, if this concept exists, and it was written by this particular by Edelman, who is a Nobel Prize in medicine, and they were discussing kind of a definition of complexity of neural networks in order to define so to find a way to describe how consciousness arises from the brain. Okay, so I will not really enter into this. It's almost a philosophical say discussion. And anyway, they wrote an interesting definition of complexity of a random system, and he proposed me to work on this definition since it seems to be nice for mathematicians, and there was no work, no rigorous work on this, and so I will describe you this definition in a second. Now, the main idea is that if you have a random system, which would be a family of random variables, it should be like the brain, say, considered as a collection of neurons which are connected to each other, and which of course work, so every neuron works on its own, does its business, but it's also interconnected with the others, and so a complex system should display two behaviors at the same time. So the first is a differentiation, meaning that every neuron has to be able to perform freely some task, but also some kind of integration, which means in this case so correlation on a global scale. Now we want to explore this concept and in particular try to understand what it means for a random system to have a high complexity according to the definition given by these biologists. Okay, so very brief introduction to the theory of entropy. So we are going to consider discrete random variables also, which means there is a finite set, perhaps large but finite. So this is not large, but at least it's finite. And we will consider random variables. And then the entropy is very classically defined as minus the sum of this functional of the probabilities that the variables takes its possible values with this convention. Okay. Now the entropy is considered to be a measure of the randomness contained in X. So let me remind you that we have two bounds. So the entropy is always non-negative, and it's always bounded by the log of the cardinal number of values that the variable can assume. And the two extremes are assumed only in very particular cases. So the entropy is zero if and only if X is deterministic. Okay, so its law is a Dirac mass in one value, and it's maximal if and only if X is uniform. So if you think of amount of randomness, so the deterministic case, of course, is a minimal amount of randomness, and uniform is so say if you don't want to talk about random, you talk about uncertainty. Now, the uniform is the most uncertain outcome you can have among random variables. Okay. So, what happens if you take two random variables? Now you have a vector, but this is again a discrete random variable, so you can define in the same way its entropy, and you have two easy bounds. Again, the two bounds are assumed only in special situations. So the entropy of xy is equal to the entropy of x if and only if y is a function of x, which means that y doesn't add any additional randomness to x. And so this is always bounded by the sum, and it's equal to the sum if and only if the two are independent.
Just to avoid confusion,
yeah.
could you tell me how you define entropy of the pair?
So it's the sum.
So just you take it as an e squared value.
xy. Okay, so you have probability that
okay.
pxy log pxy. Okay, and there is a minus. Okay, so it's the vector is again a discrete random variable which takes as values the product of the values of the two components. Okay, and now we can define the mutual information like this. So by this inequality, this is going to be always greater or equal than 0. And okay, because of this property, we see that the mutual information is 0 if and only if the variables are independent, and so it will be positive as soon as they are not independent. So it's in a sense a measure of the amount of dependence of the two variables. So you can see it like this with some a Venn diagram. I think this was called in high school. So this is x, this is y, and this is the randomness which is shared by the two variables in some sense. Okay, so the mutual information measures this intersection of randomness. Again, it's 0 when the two are independent. Now let's come to the definition of the biologists. So they consider a network in. Okay, this is not really the typical definition of a network. So these are the neurons. Okay, and each neuron can take some state. Let's say 0, 1. So this will be the state of the first neuron, and this is the nth neuron. And we suppose that the whole family is random. Okay, so this takes values into 0, 1 to the n. And it's a random vector. All right? So typically a neural network is a graph. But they do not really consider a geometry on this space. They rather consider correlations between the states of the single neurons. Okay, and so we are going to look for arbitrary measures which correlate in arbitrary way these variables, and compute some functionals of this law. Okay, so instead of really drawing edges between the neurons, you will just ask yourself, so this will take some value. So what is the effect of the decision of x1 on x2, x3 up to xn? Okay, so how much does this influence the rest of the system? And what is the choice of this influence which makes the system complex? Okay, so okay, this is a definition which is somewhat arbitrary, but it was interesting for these biologists. So they do the following construction. They consider a bipartition of the system in two subfamilies. So this is S and this is S complement. Okay, and they consider this as two big random variables, and they compute the mutual information between these two big random variables. So how much are the state of this subfamily and the state of this subfamily correlated? Are they independent? Are they dependent? How much do they depend from each other? And so you see they do this. They compute the mutual information between two subfamilies and compute an average. So they choose to fix essentially to choose uniformly the size of this family, and then among all possible families choose uniformly, so with this binomial factor. Okay, so later I will tell you one can generalize this, but let me stick to this example for some time. All right, so I think the definition is rather clear. Now notice that, okay, we have this convention, doesn't really matter much. So the neural complexity is 0 whenever this is clear, whenever all these mutual informations are 0, and this is true only if X is independent. And among these independent families, you will select two special cases. One, when they are as random as possible. So for instance, take Bernoulli random variables and all independent. And this is a situation of extreme, if you want, independence that you can also describe as complete chaos. Okay, and so you understand this is not a very complex system. If every neuron does whatever it wants without affecting the others, there's no complexity in the system. And the other extreme is complete order, for instance, a deterministic family of states. Okay, and this is the opposite extreme. It's not very complex either. So, okay, if you want before going on, the question in this talk is, okay, it's easy to find minimal complexity systems. So how can you find maximal complexity systems, or at least systems with high complexity? So we modify a little bit the definition by dividing by n+1. So this is not revolutionary, but it has an important consequence. So that, okay, with this normalization, the functional becomes additive on independent systems. Okay. This was not relevant for the biologists because they do not really want to change the number of neurons. They fix a number and then try to make simulations on this. So, but of course we want to take limits and so on. So it is natural to have a nice normalization, and this seems to be 1. So actually,
but the first property should be valid without the normalization.
Oh, no, of course. So the first property is simple, just invariance under permutations, and it just depends on the fact that the coefficients do not depend on S, but only on the cardinality of S. And there is another nice property that with this normalization, the coefficients sum to 1. So, of course, if you are a probabilist, this is the best possible choice. But okay, this additivity property is important because it allows you already to build systems which grow, so whose complexity grows linearly with the size. Okay, so by additivity, now it's enough to take independent copies of a fixed system, and then the complexity will grow linearly with the size. And this is important for this slide. So now, since we are mathematicians, let's give some precise question and definition. So we are going to try to understand what happens when you try to maximize this functional. Okay, so you fix n, and you take an arbitrary, again, the variable here of our functional, so is the law of this family. Okay, so we try to maximize this functional over families of random variables. And it's so easy to see by superadditivity that this quantity grows linearly. So I didn't write it, but this limit, this supremum, are strictly between 0 and plus infinity. So this is a non-trivial limit. Now, several questions. So first, what is this limit? Okay, so what's the optimal speed of growth of this quantity? And then, so if you fix n, are you able to describe the exact maximizers? Because we'll see that they are not unique. And if you cannot do that, can you at least say what looks like, what systems look like if they are close to this maximum, to this supreme, okay, in the limit? So an approximate maximizer is a sequence which has the correct growth at infinity, even if it does not necessarily exactly maximize at fixed n. Okay?
Is it clear that your supremum is finite?
It's yes, so it's not difficult from this expression, because this is bounded by like n over 2 times some log. So there is some easy bound, yes. Okay, about maximizer. Actually, we do not know much about the maximizer. It seems to be a difficult question, and so we decided that it was not the most interesting question. But at least for n equal to 2 and 3, we can so describe the maximizers. So of course this is not very interesting, but at least it explains a little bit what this should be. So you can in fact find explicit maximizers, because you can maximize separately every term of the sum. Okay, so for n equal to 3, for instance, there are just 3 sums here, and 3 terms, sorry, in the sum, and you can maximize them separately, and it turns out that the maximizers are of this kind. So you take x1, x2, Bernoulli 1/2 independent, and x3 equal to x1 plus x2 mod 2. Okay, and this is a very well-known example in so when one teaches elementary probability theory. This is a family of 3 variables which are pairwise independent but not globally independent. Okay, and this explains what happens. I told you at the beginning, you should have local independence and global dependence. All right, and so this is a very trivial example of this kind of system. Okay, so if you take a small portion of the system, it looks like an independent system, but if you take the whole of it, you see some correlation appearing. So already for n equal to 4, we do not know what exact maximizers are, and so why? Because because you will see. So you cannot do whatever you want with entropies. So in some sense, there are constraints which are hidden in the system. They are not easy to handle. Okay. So anyway, we have a couple of results which are anyway interesting. So a natural property because of the invariance under permutations would be that the maximizers are exchangeable, okay? Which means the law is invariant under permutation of the neurons. Actually, it turns out that this is not the case. So if you take exchangeable families and you maximize the functional, then this supremum grows much less than linearly. So if you divide by n, this goes to 0. So it does not approach the maximum. And this means in particular that exact maximizers are neither unique nor exchangeable. Okay? Because if you have one, you permute it, the value is the same, but you get another law because it should not be exchangeable, and so you don't have uniqueness, which is related to the fact that our functional is not concave. It's neither concave nor convex, and so this also shows that the problem of maximization is not trivial, right?
You know something about the asymptotics of the maximizers?
Yeah. So yes. I will come to this in a second. Okay. So it's not a concave, neither convex, but here we are maximizing, so not concave problem. And in particular, we have non-uniqueness of maximizers, and also we can say something about the support of the law. Okay, the support is a subset of this space. We know that it cannot be large. Okay, we have a bound, uniform bound on this size, but okay, this is it's okay. Okay, so the first property is an example of spontaneous symmetry breaking. Physicists call this kind of lack of symmetry in a symmetric problem. Okay, now let me come to approximate maximizers, which are more or less perhaps the most interesting part of this work. Now we have some natural bounds. Okay, we can say that if you have any system growing in size with n, then the complexity will be bounded by this quantity as n goes to infinity. Now, so this is a bound. Now the question would be, can we saturate this bound? Okay, can we get close to this 1/4? Actually, I'm going to generalize this question to a more complex one. So I want to plot two quantities, two functionals of the system. So the total entropy, which is to be normalized like this. So log 2 is just because I chose 0, 1. This also can be, if I choose 0 to I don't know, d minus 1, then I would put d here. So this is not very important. Anyway, I stick to the initial choice. And so this is the correct normalization of these two quantities because they grow with n, at least over independent systems. And so I want to plot these two quantities for any x, for any system of n neurons. Now, the first bound says that this is at most, for any possible value, I cannot exceed 1/4 in complexity. And now, the second is telling you that if this quantity is close to x, then the complexity will be below this parabola. Okay, x1 minus x. And so, okay, this is the allowed region. And now the question is, can you approach the boundary of this region? Of course, I already said that it's easy to find zero complexity systems, but can you find systems with these values of I and h at least asymptotically? So this is more difficult, and this is the main result, that indeed it is possible. Okay, so you can find systems which, as n goes to infinity, approach any point of this curve. Okay, now I.
Isn't it the case that the number of E is 2? Or
You mean n?
no. So the state, so each state.
Yes. So this is, as I said,
1K.
I could consider a case like d minus 1, and then I would have log d.
Yeah.
This would be the only difference.
Yeah.
The rest would be the same. Yes.
So you said that you could have easy examples where I of x is 0, but can you have I of x is 0 for any value?
Yes. This is easy. It's enough to consider Bernoulli with a different parameter, and this varies the entropy. And if you are independent, the complexity is always 0. Thanks for the question. Okay, so this is the main result. So you have to show, you have to provide systems which approach this maximal complexity given the asymptotic entropy. Now, so it turns out that it's possible to find this with a randomization. Okay, so it's like the Erdős program. If you want to find something, okay, it's easier to find a random element chosen so appropriately, which does what you want almost surely when n goes to infinity. Okay, so this is what we are going to do. We are going to construct them. So random families. So, but there are two levels of randomness in the sense that so you consider the law of this family as a measure mu. Now, law will be of x equal to mu. So this is a probability measure on this space. And then we are going to consider random measures chosen in an appropriate way. So actually, we have discovered after having the idea that this construction is known is very well known in information theory because it's related to Shannon error correct. So the concept of error correcting code, and but we use it in a different way. But this is known in the theory of Shannon. Okay, let me explain this. N is your parameter, so the size of the system. M is essentially it's going to be x times n. So m is integer part of x n. Okay, so you have two parameters in your formula. So you want to build a probability measure on this space. Okay, you're going to do the following. You're going to select randomly a support, and then you're going to take the uniform measure on this support. Okay, so selecting a support means selecting some configuration. So you're going to select a certain amount of sequences of 0 ones, okay, and then put uniform mass on these sequences. So this is described as follows. So you see, you have a certain family of IID variables, each uniformly distributed on lambda n, which is 0, 1 to the n. Okay, you take 2 to the m variables. So you take 2 to the m points in the configuration space. You choose them randomly, and then you put uniform masses on these. Okay, this gives you a certain probability measure mu that you will consider as the low of your random family. Okay, so there are two levels of randomness, and so the result is that almost surely in these families of randomly chosen configurations, you have the correct behavior. So you have that the entropy is the correct entropy asymptotically, and the complexity is the correct complexity asymptotically. Okay, perhaps I can give you an explanation of this result. Where is the tracer? Here. So then I will try to show you how you make computations, but I want to try to explain why this is plausible. Okay, so you can associate to this construction a binary tree. So 0, 1 to the n is made of sequences. So let's say omega 1, omega n. Okay, and each corresponds to the value of one variable. Okay, so this is the value of x1, of x2, up to xn. Okay. Now, when you choose the first, variable, you choose the first value. Okay. So you have two choices, of course, 0 and 1. Okay. So this fixes the value of x1, of omega 1. Yeah. Okay. Then you have another choice here, which fixes the value of omega 2. So this is omega 1, 0, omega 2, 0, and this is omega 1, 0, omega 2, 1, and so on. Okay, and you can go on with the subsequent choices. So you do this n times. So at the end, you have here 2 to the n points, which are exactly the configurations of this kind. Okay, so at the end here you will have 2 to the n configuration. Now my random construction consists in choosing points uniformly in this family. Okay, I'm going to select 2 to the m points here at the end of my tree. So I select 2 to the m configurations, as I said, uniformly and independently of each other. Okay, so I will choose, for instance, this. I will choose this. I don't know this. Okay, I could choose twice this, but this will happen with small probability, so this doesn't it's not a problem. Okay. Now this gives me the low of my family, right? Because I know the probability of having, for instance, 0, 0, 0, 0 is 2 to the minus n. Okay, because I chose this. 0, 0, 0, 1 has probability 0. Okay, so I made some choice. Now, if I walk back on the tree, I'm going to reconstruct the marginal laws. So, for instance, this, if I want to compute the probability under mu that I have chosen omega 1, 0 until omega n minus 1 without considering omega n. So this is in this node I have to put the sum of the masses which are here. Okay, and here I will sum and find this, sum find this, sum find this. Okay, and then I go on and walk back along the tree, summing the masses and finding probabilities in each node. So let me give you this example. I would like to prove, so to compute the probability that omega 1 is 0. Okay, so what is the right here, mu of omega 1 0? So this corresponds to the sum of all the masses which are in this upper half of the tree. Okay, and now what does this mean? So this means that I have to take so the upper half of this configuration space and compute how many configurations I chose in the first in this step. And okay, this is so for one variable to be in the upper half of the tree, this is a Bernoulli 1/2 variable. Okay, so I am summing m Bernoulli 1/2 variables. So this is a binomial. Okay, so this is 1/2 to the m, which is the mass of each configuration, a binomial of parameters 2 to the m 1/2. Okay, and this is by the Gaussian approximation, if you will, by the law of large numbers. If m is large, this is almost 1/2. Okay, and the same is true for the other omega 1 equal to 1. Okay, so both here are more or less 1/2, not exactly, but very close to when m is large. Now, if I do the same, omega 1 is something, whatever, 1, up to omega k, something equal to 0. So this is going to be, let's see. So this is going to be, okay, let's do, so let's do this for 2, and then it will be easy to generalize. So omega 1 equal to 1, omega 2 equal to 0, for instance. So this corresponds to a quarter of the tree. So by the same argument, this is going to be 1/2 to the m, a binomial. So I have 2 to the m Bernoulli, but each has success probability 1/4, and so this is 1/4. And again, this, by the law of large numbers, is essentially 1/4. Okay, and then if I take k with k small, you can see that this becomes 1/2 to the k. So almost by exactly the same argument. So this means that k random variables with k fixed and m large look like independent Bernoulli. Okay, this is by the law of large numbers and a simple argument. So again, this is exact, and this is just an approximation. But now, what happens if we are so if you take a lot of variables, so k close to, so larger than m, and so between m and n. In fact, this completely breaks down. It's not at all this kind of approximation. Why? Because before getting to m, what happens is that these masses do not have time to coalesce with each other in some sense. So the most likely thing is that this mass will travel through the tree without meeting anybody else. Okay, and so between n and m, this will be still more or less a family of 2 to the m masses, more or less isolated. Okay, and so there is no sum, so there is no effect of this kind, and this means that, so you see, when you don't coalesce masses here, it means that this choice is a deterministic choice given this one. So once you are here, you are sure that you will go here because the probability of being here is 0. Okay? So in some sense, you are in the regime where the additional variables are deterministic functions of the ones you have already. So far from independence, it's the opposite situation. Okay, so you see that there is a very sharp transition from an independent situation for small subfamilies of variables to much more dependent situations where when you take a lot of variables in your system. Okay, so and I will try to show you that this is exactly the behavior that causes this fact. Now, okay, perhaps this is going to be a little bit too technical, but I know I do not want to kill you with too many technicalities. So this is actually the best explanation I can give you. But so let me see what. No, okay. Please, I will ask you for an additional effort. So to be perhaps more precise than that, so I can rewrite my functional in this way. So it's you see something which looks like an integral from 0 to 1 of a function. Okay, so I will write this. You see, this is something like 2 integral from 0 to 1 of h dx minus h of 1. Okay, so where h is this kind of, so we call this entropy profile. It is an average of the entropies of families with a fixed size k, and then normalized by n. Okay, so we plot this kind of functions, which again, so at these points, so k over n, we plot this average entropy of a family with size k. Now this function has to satisfy some simple properties. It must be increasing, it must be 1 Lipschitz, must be don't know what, it must be concave actually, although this is not very important. And so there is a maximal possible function with okay, sorry, and h of 1 is the total entropy, which is exactly this quantity that I want to plot. So h of 1, this is the total entropies. So in some sense, h of 1 is fixed, because I want it to be close to small x in the limit. So there is an optimal function, which is this one. So it's y inf x, okay, which is a maximal function which will be 1 Lipschitz and increasing with fixed values, with fixed value at 1. So you see, if you want to maximize this, it looks like you are trying to maximize this functional over this class of functions. Okay, it's not quite this, because you cannot, this is the main problem of the whole story. You cannot really realize any function you want as the profile entropy of some system. So this is a profile entropy, an entropy profile satisfies these properties. But if you take any function which is one Lipschitz and increasing and concave, it's not necessarily the entropy profile of a family. But still there is a link between the two problems. So you want to maximize this functional over this class of functions, and it turns out that this is the best possible choice. But what is this? Yeah, these are the bounds which follow. So I'm sorry, I think I'm giving too many technicalities. It was not supposed to be like that. So let me try to recover my audience. What can I so yes, so you see the point, let me see what yeah, there was, okay, if you want, there is a simple bound, okay, there is a simple bound which is absolutely general and which is obtained by okay, some consideration of this kind. There is an optimal profile, and all profiles that I can find are below this one. Okay, so this gives me an upper bound. Now, it's nice to have an upper bound because now, if you take if you take the L1 distance from your upper bound, okay, this is actually just the expectation, because you see when you have a positive random variable, of course its L1 norm, it's equal to its expectation, right? So now you have a random quantity, which is the complexity of your random system, which is bounded by this optimal profile. You want to compute the L1 distance from the optimal profile, and it's enough to consider the expectation. So this is a very nice property, because it allows you to profit of the symmetries of the system. Now, what you do is you reduce the whole computation to this quantity, so which is very much related to the tree I explained you before. So you're reduced to compute something which looks like this. So the expectation of a certain function, which is x log x, of a binomial variable blah blah blah. Okay, you see the connection with the tree I gave you before, and you see you are exactly computing a functional of this kind, more or less the integral from 0 to 1 minus the value at 1 of these functions. And it turns out that this quantity has a very, very sharp transition. Before m, this grows, okay, it's here. Before m, that quantity grows linearly, apart from a very small error. And after m, it's constant, apart from a small error. Okay, so this means that your entropy profile, at least in a L1 sense, okay, this should be discussed, is very close to this up to some point, then has to go away, and then it's very close to this until the end. Okay, so this is the entropy profile you can realize, and again, this is very much what I told you here. You remember when the entropy grows in an additive way, this is equivalent to independence. So here you are in a situation where the entropy is growing linearly, which is so almost linearly, which is equivalent to almost independence. Okay, while here it becomes flat, almost flat, which is equivalent to say that whatever you add is essentially a function of what you already had before. Okay, so it's a very sharp transition from, so you have k variables here and they look almost independent. Here you have k variables, so which are a lot, and you see a lot of dependence. So you see that all these variables are a function of what came before. Okay, and this is true for any choice, not just one. So because this was the entropy profile was an average of all possible choices. So this is not true for just one particular choice of your k variables, but for any possible one. So it's really a very strong property. But
Is there a typo in the last line there? You went 2 to the k minus m or 2 to the m minus k?
here you mean?
Yeah. K is
Yeah,
bigger
you're
than
right.
m.
So this there is a minus. Thank you. Otherwise, this is quite large. While I want it to be very, very, very small. So so what I want to again to insist on is that this is a very strong property, but it is not an exact property. It's just an approximate kind of independence or dependence. Okay, so it turns out that you cannot realize a family which has exactly this property. So you take k variables up to n are independent, and m plus 1 are a function of the first n. So this is too rigid a construction. So you can do it for n equal to 3. Okay, I told you, so that example works. But if you want to do it for n large and m also large, so this is impossible. So this is the best you can hope for. And yeah, so okay, the result is that once you know this for one particular family, this is true for any other family of approximate maximizers. Okay, so this remains vaguely stated, but this value of this functional, so high values of this functional are related to this kind of sharp transition from local independence to global dependence. Okay, in a way which can be quantified with these entropy profiles and so on. And this is what somewhat the biologists describe in their works. But okay, doing simulations rather than providing true examples. And okay, so I have a couple of more slides, but I think I stop here. Thank you.
Questions, comments? Okay.
No, it's probably a silly question. When does this transition occurs? In the beginning, you have n, which is your
Yes. Okay. Thank you. So again, I fixed x, which is this. So this is fixed, Okay, and then you choose m like this. Okay, so then this transition occurs at this x. So this will be x.
But how is this x related to the original?
If you want the absolute maximum, you take x equal to 1/2. Okay, which yes, you're right. I didn't mention that this is always the case. The maximum corresponds to entropy equal to half of the possible total entropy. Okay. So again, no, thank you. Thank you. This is a good. So I told you at the beginning there are two extreme situations. One was the total chaos, which correspond to maximal entropy, and one was the total order, which was zero entropy. Okay. So this is perhaps intuitive, but it turns out that indeed the maximum complexity corresponds to half of the total possible entropy. Okay.
But in the case of n equal 3,
Yes.
then you get 2 always.
Yeah. Okay. But because, of course, again, this is true when n goes to infinity. Okay.
Okay.
So when n equal to 3, I cannot take half, but 2 is
This is important.
yeah. Yeah.
Is there any measurements or real-life data where this can be applied to, and what kind of complexity can be observed there?
Yes. So now there is a series of papers by these biologists. To be honest, I do not understand what they do. So this is due to complete absolute difference of language and okay. But so they are also very so theoretical in some sense, and they do rather numerical simulations than real data analysis. Okay, so but with people in Paris 7 in the biology department, we are trying to work together on some possible applications. But so this is as you see, just a mathematical. I don't know even these biologists what they apply this to. They also try to make examples with Gaussian measures, with things like this, to see how they can correlate their families in a clever way. But
You mean Gaussian measures instead of Bernoulli?
yes, so this is another aspect. I consider discrete variables, okay? But this is also because the entropy of a Gaussian measure can be infinite variable. So the entropy of continuous random variables is not very well behaved. It's not always positive. It's very often infinity. So it's kind of a strange.
More questions?
In terms of the measure on 0, 1 to the
Yeah.
n, this basically says make them IID, but subject to a constraint that the total number of ones is n.
Well, 2 to the n, but no, I think there are more constraints than that actually, because you see, that should be true also more if you take only n minus 1 variables, also n minus 2, also n minus 3. So it's this transition, I would say, more or less, as soon as you take more than n variables, so say significantly more than n variables, there should be only 2 to the n ones in your. So
So there are lots of.
I think that there are not just one constraint, but perhaps more than that. And anyway, it's not realized in this way, but it's an interesting suggestion, but I don't know how to really match it with. Anyway, it's not just once, you see, because here you are selecting configurations which are run, so they contain 1, 0s in a. You see. So there is something of what you say, but it's not completely precise.
Any more questions? No? So, let's thank the speaker again.
Thank you very much.